Hello, everyone. It's me, Billy Younger, with BillyYoungerPhysicsSolutions.com. I'm here to work yet a third part of a electric dipole problem. We first worked the electric dipole uh, on a problem in which we solved for the force on a 1 millicoulomb charge above the center of a dipole. The dipole had a separation distance of 6 centimeters between the two charges of plus or minus 1.11 nanocoulomb. And then above the midpoint, 4 centimeters above that, was a charge 1.00 millicoulombs. And we worked out the force at that point. Then we worked out the force if that same charge was put above the positive charge, a distance 4 centimeters above it, and of course, along a distance perpendicular to the dipole line. And now this is the third one where we're going to do the same thing as we did, only we're going to first calculate the electric field and then use the electric field to figure out what the force would be if we put that 1 millicoulomb charge directly 4 centimeters above the center. So let us get started. I'm going to go ahead and share my iPad screen, and I'll read the problem and get started by drawing a picture and doing the calculations. So what we have here is an electric dipole is constructed by a charge Q1 equals negative 1.11 nanocoulomb, separated by a distance of 6.00 centimeters from the second charge Q2 equals positive 1.11 nanocoulomb. And we're asking A, what is the electric field 4.00 centimeters above the midpoint of the dipole? And B, what would be the force on a charge Q equals 1.00 millicoulombs at that point above the midpoint? So that's what we're going to do. I'm going to start off by drawing a diagram, and I'm going to go ahead and include a coordinate system so we can all agree on what's the x-axis, what's the y-axis, that sort of thing. I'm going to say that this right here is the positive x-axis. I'm going to say this is the positive y-axis. And I'm going to say that this chart, or this point right here, is 4.00 centimeters above the midpoint. And then I'm going to say that this point right here and this point right here is where the two charges are. So this one's going to be Q1 equals negative 1.11 nanocoulomb. And this one's going to be Q2 equals positive 1.11 nanocoulomb. And of course, later we'll work with a charge Q, but right now we're just talking about a point P at which we wish to know the electric field. So our solution is, now to do the solution, we're going to actually need some information. What we did learn was that the electric field E can be defined as well, we do take a limit in some sense as, let's say, Q approaches 0 of F over Q, and that's a vector equation. And of course, we're taking the limit as Q approaches 0 specifically because we want the charge little q that we think is going to be ultimately affecting the charge, the electric field, and ultimately feeling the force. We think we want to try to minimize the effect it would have on the existing electric field. So that's what we're talking about. At least from an experimental setup point, we have to try to consider a charge getting smaller and smaller so that it has negligible effect on the field created by the other charge. In terms of Coulomb's law, that ends up getting us at least one form would be K Q over R squared. That's the actual formula. Of course, that also tells us that the force is equal to the charge times the electric field. So once we actually get the electric field, we can just multiply it by whatever charge we want to put at point P, and that will give us the actual force. Of course, we also need to realize that the electric force, or the electric field, the total one at P, which I'll just call E sub P, has got to be the electric field at P due to charge 1 plus the electric field at P due to charge 2. And of course, that means the x components of the electric field at P is the sum of the x components due to the electric field at P from 1 plus the electric field at P from 2, and the same thing with the y components. So let us go ahead and get started. I'm going to start off by calculating the magnitude of the electric field. The magnitude of the electric field at P due to 1 is equal to 8.998 times 10 to the ninth. I'm going to leave off the units this time. We've worked in 2 previous examples showing all the units. It's not critical that we show it now. I'm actually talking about the electric field created by Q1 at this point. So I'm going to put in 1.11 times 10 to the negative 9 coulombs. Notice I did not put in the sign. Again, Coulomb's law for force. I don't put in the signs for the charges. Coulomb's law for the electric field. I do not put in the signs for the charges. And then all of that, of course, is going to be divided by the distance between the actual charge Q1 and the point P. Now, we did, even though I didn't write it on the diagram, let me do it now. This is 3.00 centimeters, and this too is 3.00 centimeters. And then this distance above is 4.00 centimeters. What that gives us, of course, is a 3, 4, 5 triangle that's quite nice and easy to deal with. And it tells us that the distance between Q1 and P is in fact 5 centimeters. So I'm going to write 5.00. Actually, I'm going to go back and put it in black. So it's going to be 5.00 times 10 to the negative 2 meters, because it obviously has to be in the base units. And actually, I put a Coulomb there, and I put a meter here, both of which I said I was going to leave off because we're not showing the units. So to be consistent, let me go ahead and do that. And then I got to square all this. So when I go to calculate it, I'm going to go ahead and turn on my calculator. I'm going to say 8.998 exponent 10 to the ninth times 1.11 times 10 to the negative ninth. And then I'm going to divide all that by 5 times 10 to the negative 2. And that quantity is going to be squared. And that's going to give me 3,995 newtons. And I'll call it 95.1. Actually, by the way, this is newtons per coulomb, not newtons. You can tell because remember the force was K Q1 Q2 over R squared. This is K Q over R squared. So obviously, since the last one was newtons, if I've got one less coulomb in the top, it's going to be newtons per coulomb. We'll also later learn that that's consistent with volts per meter. So that's ultimately where we're going. These 2 digits, the 5 and the 1, are not sig figs. Now we've got to actually figure out, since in fact E is an electric field, which is a vector quantity, we've got to actually figure out a magnitude and direction. Now what we know is if we put a positive charge, and this is what you're supposed to use to figure out the direction of an electric field, is you imagine a positive test charge at the location that you're trying to calculate the electric field, and you imagine in which direction would it be compelled to move. In other words, in which direction would a force on a positive charge placed at P, and what direction would that force point? Now, since it's a positive charge, if we put it at P, it would actually be attracted to Q1 because that's a negative charge. And in fact, the force and therefore the electric field would both be parallel to the hypotenuse there. So this is going to be the electric field at P due to 1. That's the direction of it. You can notice that the angle right here, that angle is in fact opposite the 3 centimeters and it's adjacent to the 4 centimeters. And that, of course, means it's 36.87 degrees. So this angle right here is 36.87 degrees. And we can see, for instance, that the y component is in fact negative, and the x component is in fact negative as well. And we can get the x and y components as follows. So EP P1 sub x, and actually I don't need a vector symbol on that, is going to be equal to, I'm forcing it negative because that's what the physics of it tells me. I'm going to actually realize that the sine of 36.87 is going to be the x component divided by the hypotenuse, which is the magnitude we already calculated. So just to clarify, let me write that down here. This is EP1 sub x, and this is EP1 sub y, like that. So we just have all those. The next one's going to be obviously a little bit more problematic just because we got all these drawings on them, but we'll deal with that when we come to it. So now I'm going to take this let me go back to my black. I'm going to take this 3,995.1 Newton per Coulomb electric field, and I'm going to multiply that times the sine of 36.87 degrees. And that's going to, of course, I got to force the negative again, but that's going to give us 3995.1 times sine 36.87, and that gives me 2397.1 negative. And that's newtons per coulomb again. Again, we only had 3 sig figs, so I'm underlining the 7 and the 1, but that gives it to us. Now I'm going to do EP1y. That also is a negative, and it's going to be 3995.1 newtons per coulomb times the cosine of 36.87 degrees. And again, I got to force that negative. So 3995.1 times cosine 36.87 gives me 3,196.1. So negative 3,196.1 newtons per coulomb. Again, underlining the 6 and the 1 because they're not sig figs. Now we can do EP2, and that's going to be 8.998 times 10 to the 9th. I'm going to put the units here because I realize now that y'all hadn't verified that the units are newtons per coulomb. So the units for the K is newtons times meters squared per coulomb squared. The magnitude of the charge Q2 is 1.11 times 10 to the negative 9 coulombs. You can clearly see that I have Newton meters squared per coulombs now that that Q's in there. And then when I divide it by 5.00 times 10 to the negative 2 meters, and that's squared, you're of course going to get just meters canceling out. So we're left with just newtons per coulomb as advertised. So this force is going to be, as you can tell from the formula above, it's the exact same numbers. So it's still going to be 3995.1 newtons per coulomb. Again, the 5 and the 1 are not sig figs. Now, in this case, we imagine again a positive test charge at point P, and that positive test charge would be repelled by this charge Q2. So we actually expect the positive test charge to feel a force acting. I'm going to use blue here in hopes that it shows up a little better. So it'll be along this line, and the force would actually be, or the electric field would actually be there. So this is going to be EP2, that force right there. You can again see, of course, that we're going to have a positive y component this time. So I'm going to put that in blue. And we're still going to have a negative y component. So I'm going to put that in red, or excuse me, a negative x component. So I'm going to put that in red. Okay. So now you can see that this guy right here by the y is EP2 2 sub y, and the red one up the top is EP2 sub 1, or excuse me, sub x. So EP2 sub x is that guy. Obviously, this angle right here, let's use a marker. This angle right here, notice, is what we call a vertical angle because you can see it across a vertex. There's the vertex. So this angle and this angle are the same. This angle we know is 36.87. So this angle is also going to be 36.87. So again, this is what vertical angles look like. This guy and this guy, but also this guy and this guy, because they too are across the same vertex. All right, so 36.87 is the angle that we know to look for. I'm going to go ahead and compute the y components and the x component. I'm going to start off with the x component, of course. So this is EP2 sub x, which we decided is obviously negative. That's going to be 3995.1 newtons per Coulomb times, in this case, the x component is still going to be sine, so it's going to be sine 36.87 degrees, and we know, of course, that's going to be negative 2397.1 newtons per Coulomb for the x component. The y component is actually going to be positive, so I'm going to put a positive here. This is again going to be 3995.1 newtons per Coulomb, and this one will be cosine 36.87 degrees. And of course, you can see that's the exact same numbers as we did for the y component, only now it's positive. So this number is going to be 3196.1 newtons per Coulomb, again with the 6 and the 1 not being the same, or excuse me, not being sig figs. So what I can say is the x component of the entire electric field is equal to the sum of the two x components, which would be negative 2397.1 plus negative 2397.1, which is basically 2397.1 times 2 with a negative, of course, and that gives me 4794.2. So the 4 and the 2 are also not sig figs. Okay, and that clearly gives us a negative for the total result. Now we can do EP sub y, and these two, you can see they're just going to cancel each other out. It's negative 3196.1 plus positive 3196.1, and that gives us 0.00 newtons per Coulomb there. So we now have the electric field. We can state the electric field. It's purely in the negative x direction. So I'm going to say EP is equal to. I'm first going to state the magnitude and direction terminology. So this is going to be 479.4.2 newtons per Coulomb. It points in the negative x direction, which is an angle of 180 degrees from standard position. So I'm going to say at 180 degrees. Of course, you can also write this as negative 4794.2 newtons per Coulomb. And then you just put an x hat with that. And that means the same thing, at least for my students that are in the calculus-based physics class. Okay, so that's what our electric field is. That's not all that helpful in comparison and comparing it to the previous problem, but what will be helpful is now that was just part A, but part B is going to be F is just Q times E, and what we know is the Q I plan on putting there is 1.00 millicoulombs. So if you multiply a vector times a scalar, you're really, if the scalar is positive, you're not changing the direction at all, but you are multiplying the magnitudes. So in this case, the magnitude is 1 times 10 to the negative third. When I do that, I'm going to get F is equal to, basically, it's just going to move the decimal 3 places to the left. So that'd be 4.7942. And now it's newtons per coulombs times a coulomb. So that just gives you flat newtons. And that's at 180 degrees. So that's one way of stating it. Another way we could state it, of course, is 4.7942 newtons in the negative x hat or I hat direction. So that is the answer to part B. That's part B there. And notice all I did was took the number immediately above the 4,700, or excuse me, 4,794.2. I just took that and multiplied it by 1.00 times 10 to the negative third. So that should be done correctly. Now, if we look back at what we did in the first example of the series, what we'll see is we got 4.7942 newtons at 180 degrees, or negative 4.7942 newtons in the I hat or in the X hat direction. So this is exactly the same result we got before, only I think you might consider it maybe slightly easier, but not a whole lot. It's still, it's still pretty much the same math that happened. So that's it for this problem. I hope that helps you, and have a good day. I'm signing out. Let's start with stopping my sharing and then ending my Zoom meeting. Have a good day.